Okay, so it's a great pleasure to introduce Gregory Pearlstein, who will speak on holomorphic bisectional curvature and applications to deformations and rigidity for VMHS.
All right. Well, thanks to the organizers. It's always good to talk to Ludmil and all Voisin, Griffiths, Carlos, and everyone else. Okay, so the motivation for this, so I also apologize, maybe this is a little bit far from rationality, but it's the closest thing I have that's recent. Okay, so the motivation for this is we're going to start off with a smooth projective curve S bar and a finite set of points sigma. And okay, so then of course we'll just let S be the complement. And now we are going to consider a non-constant holomorphic map mu from S into the moduli space of curves. And we're going to require that the genus be greater than 1. Okay, so in 1971, I think it is, S. Arakelov showed that mu is rigid if it's non-constant. Okay, so in other words, now this rigidity result is kind of fixing the, it's fixing the S bar, the sigma, and of course the target. So it's rigidity with fixed source and target. Now, of course, the first thing you might try and do is you might try and say, well, if I have a smooth curve C, then I could kind of just replace it with the Jacobian. So instead of doing what Arakelov was doing and considering maps to MG, you could instead consider this period map from S into AG and ask, is this rigid? So maybe if you allow yourself to be a bit more flexible and instead of insisting on having a curve, you replace it by the abelian variety, then maybe you can deform it. And so in 1983, I think it is, Faltings answered this question. And so, okay. So his answer is the following. So what you want to do is you want to compute the infinitesimal deformation space of this. And he showed, okay, so now this AG, right? It's what? It's the quotient of some Siegel over half space by some monodromy group gamma. I apologize, this thing kind of goes in and out of focus. Okay, so the infinitesimal deformations, you can identify it with these monodromy equivariant sections of type -1, -1. And so in particular, if F is non-constant, then it's going to be rigid if you can show that this is like pure of type 0, 0. So that's Faltings' result. And I should also say in dimension 8, there are non-rigid examples. Okay, so that's the kind of, oh no, I should say. Okay, so this is joint work with Chris Peters. Oh, you can't see that. This is joint work with Chris Peters, I should have said, and it's on the archive. Okay, so now getting back to the result of my co-author. So of course, there's no reason to stick with AG. You might as well just take F from some S into D mod gamma. The period map is some variation of Hodge structure, but I'm always going to be fixing the monodromy. Okay, so no messing with the monodromy group there. Okay, so I could take my map from S into D mod gamma, and then what Chris showed is, again, that the space of infinitesimal deformations is, again, this space of monodromy equivariant sections of type -1, -1. Okay, so any questions so far? And for people in places where the time difference is very large from Miami. So I guess I should thank you for bearing with us. Okay. So now the next thing that we want to do is I want to say, so in 1977, okay, there are various spellings of this name, but I think you need this one, kind of, if you want to find this actual reference. So this is about Mixtorelli theorems. So what he discovered was he constructed a family of surfaces X to S, and the generic member of this family has H20 equals 1, H11 is 19. It's simply connected, and this has positive dimensional fibers of the period map. Okay, so how do we construct this surface? Well, it will be a Galois Z2 cross Z2 cover of P2 branched on 2 cubics plus a line. So here we go. So F and G are my 2 cubics. My line, I might as well call it X0 equals 0. So in terms of equations, I have to go to P1, 2, 2, 3, 3. So this 1 is going to be the X0, and the other 2 degree 2 terms are going to be the kind of other coordinates. All right, and then it's a double cover branched along these 2 things. So it's Z2, Z3 squared is F, Z4 squared is G. Okay, so these, and this has a nice Galois cover, Z2 cross Z2 to P2. And one thing that's important about these things is that, so this period map that I would get by considering these types of surfaces, maybe I should have called this like script X to keep it separate from the X that I'm using here. So X has a unique canonical curve. Y, and I'll tell you exactly what it is. It's just you set X0 equal to 0. Okay, so now I think this is 1984. Okay, so move this up. So Letizia proved the following result. So if I have X and X prime are generic, like I said, there's more than one way of writing this Russian name in English. So if X and X prime are generic Kunev surfaces, and Y and Y prime are the divisors, of course, on those curves. So he uses the word polarized mixed Hodge structure. I mean, he really means graded polarized in the language I'm going to be using later. Okay, so if the mixed Hodge structures on H2 of X minus Y and H2 of X prime minus Y prime are isomorphic, then X and X prime are isomorphic. Okay, so this is kind of a Mixtorelli theorem. So we managed to fix these positive dimensional fibers by just removing the canonical curve. Okay, so now we would like another example of some Mixtorelli theorems. So this goes under the kind of rubric that you start off with X as, let's say, smooth projective. And then instead of thinking about the fundamental group, well, you can form the group ring pi1 of X. Maybe make that a big X so you can see the difference. You can form the group ring, and then of course you can map that to Z. And so the kernel of that is this augmentation ideal. And then you want to look, you can look at quotients. So these will be finite dimensional again. So if you take J squared here, you're just going to be getting back to ordinary homology. Okay, So this is another example of a kind of mixed Torelli theorem. This is due to Pearlstein and Richard Hayne. Okay, and so it basically, okay, I should move up a little bit so you don't have that little box there. Okay, so it says that if you have smooth projected curves, then up to some finite bit of exceptions, if you have a ring homomorphism of between these two quotients of the fundamental group, which preserves the mixed Hodge structure, then they're actually biholomorphic. Okay, so these are mixed Torelli theorems. And I guess I should also mention Senpai Asui and many of his co-workers in Japan studied these quite extensively. So there's quite a lot of examples of these kinds of mixed Torelli theorems. So questions? So far, so good? Okay. All right. So now I will try to state my result as soon as possible, but now stating the result as soon as possible means not setting up all of the notation. Okay, so we have a fair number of results, but maybe the strongest ones go when I have a mixed Hodge structures which have like two adjacent weights. So it has weight A and weight A minus 1. Okay, so since this is about rationality, this is why I kind of chose this topic. So I guess we can let X be smooth, and all of this is over C, of course. This is smooth projective variety, dimension D plus 1, Y and X, that will be a smooth divisor. And then, of course, we'll let U be the complement, X minus Y. So then, of course, we have our standard little sequence. So here we see exactly what we wanted. This will be weight D plus 1. This will be weight 2D because there's a shift by minus 1 there. And the cohomology of U sits in between them. And now maybe I'll give one consequence of our main result, and then I'm going to explain a little bit about something in the terminology of it. Okay, so again, without trying to set up all the technical machinery, let me just state it this way. So this period map for H2D plus 1 of U is rigid. Now, of course, I have to now change X and Y in the family. Okay, so this is rigid in the minus 1 to 0 direction, which I'm going to explain in just a second. If the following two conditions hold. So I need the monodromy representation on H2D plus 1 to be irreducible. And I want the dimension of the cohomology of X to be strictly bigger than the cohomology of Y. And okay, now, if they're not equal, then of course there's a way of dualizing all of this and getting the result you want. But let's just leave that up to the reader. Okay, so if in addition I happen to know that these two pieces here are rigid, then I'll actually get a rigid period map. So now these minus 1, 0 directions, what are they? So let me just think of the case where I have a curve minus a finite number of points. So then this mixed Hodge structure, it has some kind of 1, 1 classes, which corresponds to the points that got removed, the punctures. Then it has some 1, 0 class, which corresponds to H1, 0 on the compactification, and some 0, 1 classes correspond to H0, 1 on the compactification. And then the maps of type minus 1, 0 are just those. So this gives you a condition to make this part rigid, and then if you happen to know that this part and this part are rigid, then you win. Okay. So application number 1, of course, is families of quasi-projective curves, genus G, and you need less than 2G punctures. Okay, I mean, that's just about this thing here, and you can switch it over and do singular curves with ordinary double points, if you'd like. Okay, and so now the second application that I have in mind is these x minus y's. So these are these Kanev Todorov type surfaces. So on the paper they're called Catanese, Kanev, and Todorov surfaces. Okay, because Todorov gave a generalization of what Kanev did. Okay, so this is from our paper. So if we have a family of these surfaces, and we let K sub S be the canonical curve, then this is rigid in the following cases. So first, I need that my family of canonical curves is rigid. Okay, so in the literature that Peters was using to get some of these results out, okay, the essential part of the, okay. What were the Hodge numbers of the surface before I took out the curve? It was 1, 19, 1. So that's K3. And essential part means take the transcendental part of this variation of Hodge structure. So if that's non-constant and rigid, and 3, we want the mixed period map to be an immersion. Okay, then you get rigidity. All right, so the main thing is that those Kunev surfaces, they come in a natural 12-dimensional family. And so that, you know, kind of universal family, if you'd like, is rigid. And of course, you can take any subfamily of that for which the transcendental part of that K3 variation has rank 11. Okay, so those are some examples of what we can do with this. And now for part 3, again, normal functions, you can make rigid. I'll discuss that later. And these unipotent variations in mixed Hodge structure attached to the fundamental groups of smooth varieties, you can also make those rigid. So again, and so, well, the reason that there's some space here is I should have said, all of these arguments that I'm using, I mean, they're really about the variation of mixed Hodge structures. So the key thing is that it has only these, where is it? Key thing is that it only has these 2 adjacent pieces. And the other thing that I need to get rigidity is some monodromy arguments. So I need just the variation of mixed Hodge structure has only 2 parts which are adjacent, and then I need some monodromy. And then I make all of this stuff work. All right, so any questions on that? It's good to ask questions, because like the next thing I'm going to do is I'm going to review the proof of like the rigidity theorem in the pure case. And then I'm going to tell you what types of modifications you have to make to that argument in order to get it to work in the mixed case. So this is about to get into, like, you know, a little bit of discussing the proof. So questions, Carlos, any questions? No questions? All good? Okay. Well, if we're all good, then we go on. Okay. Okay, this is just a whole bunch of stuff about Todorov surfaces. Okay. So, all right. So what are the key things that we need to make the rigidity theorem work in the pure case? Okay, good. Now it's in focus. There's some curvature computations you have to do. There's some norm estimates that you have to do. And then there's some type of monotony argument that you have to do. Okay, so, well, let's begin. So the first thing that you need to do is to compute the bisectional curvature of the period domain in horizontal direction. So let's remember here, so D is our period domain. Will be a real Lie group acting transitively on it. And the stabilizer of a point in D under GR is compact, so it has a GR invariant metric. And so now D is contained in some compact dual, D check, and the complexification of GC acts on D check. And D check is open in D check in the analytic topology. So that means that if I have a point F in D, I can identify its tangent space with a subalgebra in GC. I just take the stabilizer of F in GC and I find the complement. And like there's a very canonical way to do that using the Hodge decomposition. So now I bothered to tell you all of that because, okay, so now what is the formula for the bisectional curvature? Well, here it is. So basically I'm gonna have to take, if I wanna know what it is in directions U and V, I have to take the bracket of U and V, take their Hodge norm, and then I subtract off this corresponding thing with U bar. Okay, now, if you've seen infinitesimal variations of Hodge structure before, or you've seen Higgs bundles, then you'll know that if I'm looking at an integrable set of directions, which are the only ones I have to worry about for this problem, then U and V are going to have commutator 0. So that's very good because then I'm going to immediately get that the bisectional curvature is less than or equal to 0 because I get to kill off that term. Okay, and now the next thing I guess we'll need is some kind of Bachner type formula. Okay, and so what's it going to tell us? Okay, so it's going to tell us that del bar of the norm of V squared is the norm of duv squared minus this bisectional curvature. So this is just a very kind of general thing where we're going to have EH is some Hermitian bundle over S, and D is the Chern connection. And nu is eta of S is our holomorphic section of E. Okay. So we're going to have this. And now for us, this is going to be very good, right? Because we just calculated HFR U bar VV here. And it only has this negative term right here. Okay, so this is greater than or equal to 0, and this is going to be greater than or equal to 0. So this is going to be greater than or equal to 0. Okay. So now the next thing, so this is a consequence of Schmid's SL2 orbit theorem. And it says that if I have a polarized variation of Hodge structure over the punctured disk, and then an invariant holomorphic section of the Hodge bundle remains bounded. Okay, so, and you probably can't see that, so you should speak up. You can't see things. Okay, So now why do we care about this? So now we also happen to know that if S is quasi-projective, then a bounded plurisubharmonic function on S is constant. Okay, and now this is just a little bit of notation which I'm going to be using later. Okay. So, and this is going to have more decorations than I strictly need for right now, but it's just to have a uniform notation for it. Okay, so if H is a variation of pure Hodge structure, then this GH are just the endomorphisms of H, which are infinitesimal isometries with respect to Q. Later on, when H becomes a variation of mixed Hodge structures, then they have their endomorphisms that have to preserve the weight filtrations, and they have to induce infinitesimal isometries on curve W. Okay, but so anyway, so if H is pure, then G of H is pure. Oh, wait, 0. Oh, and there's one other remark I should have made a while ago in case somebody asks. All of these things would work for kind of Mumford-Tate domains and mixed Mumford-Tate domains, because all of these computations are more or less Lie theory. I mean, going to the Mumford-Tate domain might help you because maybe the monodromy group, you'll get a better estimate or something. So I'm not going to dwell on that. Okay. So questions? Okay. All right. So what do we get now? So if we put parts A and B together, then so we get this lemma that says if we have a polarized variation of Hodge structure over quasi-projective complex manifold S, and eta is a holomorphic section of the endomorphism bundle, which is of type -1, 1. And we're going to suppose that for all the vectors which are tangent to the image of the period map at F, which is F sub S for some point in S, we know that U bracket V is equal to 0, where V is eta of S, then this is a plurisubharmonic function. And hence it's constant. And then we'll actually get the eta is equal to 0 and U bar bracket V is equal to 0. Okay, so I basically told you the proof of this, right? Okay, so clearly KF UV is less than or equal to 0. And so that implies by my Wagner type formula that the norm of this eta sub S is plurisubharmonic. Okay, so, but then since we're on something which is quasi-projective, and we have the boundedness result coming from Schmidt, that implies that this is actually constant. Okay, so now maybe I very quickly go back to my previous page. Okay, so this is going to be 0 now. So that means that this is greater than or equal to 0, and this is greater than or equal to 0. So if this is 0, then these are both equal to 0. So this has to be 0. And we already knew we got rid of our u bracket v already, so the only term that's left is this, which also has to be equal to 0. Okay, so that's the proof of that. Okay, so now since Simpson introduced me, okay, now let's talk about Higgs bundles. Okay, so now I've only told you something about the Chern connection, right? So I'm not actually interested in the Chern connection. I'm actually interested in the Gauss-Monin connection, right? Okay, so, well, what can we do? Well, the Gauss-Monin connection breaks up as the Chern connection plus the sigma and its adjoint. And we have good formulas for those things. So in the 1, 0 part of this is this del u plus basically the adjoint action of u, and the 0, 1 part comes from the adjoint action of u bar. Okay, but now we've got everything we needed, right? Because this here is 0, because that's the Chern connection, and we're assuming that uv was, oh, you can't see that. We were assuming that uv was commuting, and then we were getting that u bar with v was equal to 0. So when we put it all together, we see that we actually get a flat connection. Okay. Oh, now maybe I should have remarked this earlier. So why am I keep complaining about like this here? So I'm going to think of a deformation of the period map. So the deformation of the period map, since GC is acting on D check, I can write my deformation in terms of elements of this endomorphism bundle. Okay, so if we put everything together, we get that if eta is a holomorphic section of type -1, and if we assume that u bracket v is equal to 0 for all vectors which are tangent to the period map, then we indeed get that our section has to be parallel with respect to the Gauss-Monin connection, and we have this u bar v equals 0. Okay. So that's kind of how we fit all of this stuff together. Now, maybe I should be really short about this. Where is the top of the page, though? Okay. Okay, so I mean, in terms of deformation theory, I mean, I'm just thinking of, I have phi from x to y. So these are complex analytic spaces. And so I want to deform that. So I'm thinking about deforming the graph of little phi. So that means I want some map big phi from x cross t to y cross t, where t comma 0 is some analytic germ. And then, of course, what do I want? I want that big phi of x comma t is so some little phi of t x t. And of course, I need that phi of x0 is phi of x. So that's what I mean by deformations. And now the tangent space to the deformations at phi, that will be H0 X pull back the tangent bundle. I mean, this is a very standard thing, but probably should say what I mean by I'm going to be talking about deformations. Okay. So now if we have a smooth and quasi-projective period map, then the space of infinitesimal deformations of F remaining horizontal is isomorphic with the flat sections of type -1, 1 of this bundle. And moreover, at a point F, in the image of the period map, if I set nu to be this 8 of F, we always have this commutation condition. Okay, now, I mean, this is really faultings, but in case somebody was going to complain about this, I thought I should put this in. Okay, I mean, the space of deformations to the period map, which keeps the source and target fixed and stay locally liftable and horizontal, it's smooth. Okay, so no weird things are going on there. Okay, so then our rigidity criterion is just what I had told you at the start of the lecture. And now finally, we have this idea of being regularly tangent. And I mean, this definition is constructed to satisfy the theorem. Okay, so your period map is rigid if either this space is 0 or F is everywhere regularly tangent. Those are the two conditions. Okay, so that ends the discussion of an outline of how you would prove rigidity for variations of pure Hodge structure. So this covers what Faltings did and what Peters generalized. So this is a good place for me to ask for if there are any questions. Questions? No? All right. Well, then that means we just go on to the next case. If there are no questions. Okay. So, I mean, the answer is you just have to change everything that you can. Unfortunately, there's a lot of things that need changing. So the first thing that's going to be a gigantic problem is that these classifying the spaces of mixed Hodge structure M, I mean, they just don't have metrics of negative holomorphic sectional curvature. I mean, that's just the way life is, right? So if I take the classifying space that corresponds to this Tate gadget with H11 and H00 is equal to 1, then M is just isomorphic to C. Now, maybe you've seen this as C star, but that would be kind of modding out by a group of isomorphisms on this. So, but anyway, it doesn't matter whether you think of it as C or C star, you're not going to get a metric with negative holomorphic sectional curvature on that. And horizontality is trivial in this example, so that won't save you either. Okay, so now I guess the next thing we should say is maybe we should actually define what this classifying space looks like. So I should kind of say what its data is. Well, okay, eventually, if I want to have decent control of my monodromy, I'm going to have some integral form. But if I just want to be a differential geometer and not worry about the monodromy for the moment, I mean, what I really need is I need a real vector space and its complexification. And then I want a mixed Hodge structure, so I want W dot, this will be an increasing filtration of VR. And now what do I need? So I can't have a polarization, but I can have graded polarizations from GER-WK tensor GER-WK to R, and they should be -1 to the K symmetric and non-degenerate. And of course, I would like some Hodge numbers, HPQ, and for this I would like HPQ to equal HQP, because these are going to be what I get on the weight graded pieces of W. So then I would like the dimension of WK to be the direct sum over P plus Q less than or equal to K of HPQ. And once I have all of this stuff, then I can let F dot, so these will be flags in VC. And what do I want? I want that F comma W is a mixed Hodge structure, which is graded, polarized by these Qs. And the other thing I, of course, want is that, let's just make it as simple as possible. I want the dimension of FP on GER-WK. That should be what? It should be the sum over A greater than or equal to P H A K minus A. All right. So that's what this classifying space M looks like. Okay, so now I should tell you a little bit more about it. So, well, the Lie group that I want to look at the elements in GLVC which preserve W. And I need that on the real, that if I go to GER-WK, for each K, I want this element to induce a real automorphism of the corresponding graded polarization. So, I mean, I don't have any information about the things which act trivially on GER-WK. So this group is kind of half real and half complex. So this unipotent part, like they get to be complex transformations. On the graded pieces, they have to be real. So, okay. So this acts transitively on, so the talk goes to 45, is that correct? For 15 minutes? Hello? Okay. Okay, so this acts transitively on M. And the problem is, though, the stabilizer GF is not compact. Okay, so that implies there's no G invariant metric. Okay. On M. Okay, so I can maybe salvage the situation by going to GR, which is G intersect GLVR. That does act with compact stabilizer, but it's not transitive. Okay, so how do we fix all of this? Okay, so there's the analog of the Hodge decomposition. This is again due to delete. And it's these summands, these IPQ summands. So in general, we don't have that IPQ bar is IQP. Those are the R-split mixed Hodge structures, which are very important to the theory, but in general, we don't get that. But so what we can do instead is we can form these spaces lambda PQ. So this is the direct sum over A less than or equal to P, B less than or equal to Q of IAB. And then these actually do satisfy lambda PQ bar is lambda QP. Okay, so we do have some kind of analog of a Hodge decomposition. Okay, so now, going on. Okay, so we have a little lemma. So if I have F in M, then that implies that M is actually equal to GR X above lambda minus 1 GC acting on F. Okay, so this doesn't act transitively and this doesn't act transitively, but together they act transitively. Now, I mean, there's no normal subgroup or any other. This is not a semi-direct product. Okay. Okay, so, so there exists a metric H on M such that B, if G belongs to GR union X of lambda minus 1 of GC, and again, this would be with respect to F and W, then that implies that LG star from TF M to TG dot F M, this is an isometry. Okay. Okay, so that's enough to calculate the curvature tensor of all of this. Now I need to move this up where you can see it. Okay, so I take my Lie algebra of GC, I break it up into a bunch of subalgebras. So where A is greater than or equal to 0 and B is less than or equal to 0, that's this part right here. That's this part right here. Okay. Then of course I have the 0, 0 part. So these two together add up to give me the stabilizer of F. So that means the part that's left over here, I can think of that as my tangent space. Okay, so I have a description of my tangent space in a fairly canonical way using Lie theory. And then my previous work with Peters says the curvature tensor is given by okay, so okay. There it is. It's a formula. It doesn't become enlightening until you try and use it to do something. But okay, so the one ingredient is just to calculate that curvature tensor, and now we have to try and use it, right? Yeah. Okay. Okay. Okay, so I could read all the details of this proposition to you, but I mean, the main thing is that if you grind away with that formula I just gave you, you can figure out what you need for your section to be plurisubharmonic. And so therefore, if it was bounded, you would again get it to be constant. Okay, so I'm skipping over a bunch of stuff there because, I mean, until you start working with it, it's, you know, hard to have any intuition for what that proposition says. Okay, so after you start working with it for a while, you figure out what's going on. So proposition 4.22 is the one I just moved off the top of the page. Okay, so if U and V commute, then this endomorphism is plurisubharmonic in the following cases. The pure case, the kind of R-split variations where you're just going in these -1, 0 directions, which I kind of already explained to you. For unipotent variations, the graded pieces are constant. So the -1, 1 directions are 0. And then you either want this giant lambda -1, -1 piece to be 0 and V to be of type -1, 0. Or you want to just be dealing with these -1, -1 directions and not dealing with these -1, 1 directions. Okay. Okay, so these come from variations of pure Hodge structure. These come from certain unipotent variations like the one I showed you from Hein and Pulte. These come from normal functions and complements of smooth divisors. This case 4, I'm not going to be giving a talk about mirror symmetry, but these are kind of like Kähler moduli. They kind of show up in there. Case 5 corresponds to higher normal functions. Type 6, which looks quite wild. This comes up in studying height pairings for higher cycles. Okay, so the upshot is that one can try and emulate everything that happened in the pure case to give you rigidity, and if you pick good geometric examples, you'll have a chance of getting rigidity. If you just say, I want anything, then well, life doesn't want to just give you anything. You have to kind of control how badly your side structure is. Okay, and I think it's probably going to take me to the end of my talk. Okay, so admissibility. Okay, so kind of embarrassed giving this talk in front of Griffiths, but okay. So for variations of pure Hodge structure, again, they have negative polar intersectional curvature along horizontal directions, and that's what implies like the existence of the limit Hodge filtration, among other things. So if, can't even see it. Okay. This is what implies the existence of limit Hodge filtration. And so we don't have that. So we have to kind of like impose a bunch of salient geometric conditions which are true in the pure case, which are salient geometric conditions which are true for all the, we have to impose a bunch of abstract conditions which capture all the salient features of the geometric case. That's what I meant to say. Okay. Okay, so, and that's what this next sentence is trying to tell me. Okay, so now the next consequence is that we actually need to build admissibility into our deformation theory and our norm estimates, but I think the remaining, okay, maybe I do one more slide and then I think I'm going to have to say that what remains is extremely technical. Okay, so okay, get it lined up correctly. Okay, so again, we're going to start with quasi-projective. We're going to take our period map for admissible variation. Then we have the analog of regular tangency in some set of directions, maybe all directions. And so this kind of second main theorem of paper is the one that tells us that if I fix a subspace, then I'm in any one of the following situations, which are the ones I explained a moment ago. Then the deformations of the period map in these alpha directions are in one-to-one correspondence with those endomorphisms of H and Q that belong to A and which are intertwined with monodrome reaction. So the upshot of that is the following equivalent. F has no horizontal deformations in those alpha directions, or there's no endomorphisms in these alpha directions intertwining the actions. The monodromy, and then that's equivalent to regular tangency. And having proved that, then you can go back and look at all of these various geometric cases I had promised earlier. So I think that's a good place for me to stop, unless I've completely misunderstood how long this talk is supposed to be.
All right, thank you very much. Any questions? Okay, if not, let's thank Greg and we'll proceed tomorrow at 9 a.m. New York time. Thank you very much.